Welcome to the last video cast on Chapter 6. We left off in this PowerPoint packet at the Pauli exclusion principle slide. And so if you'd take out your PowerPoint packet, please, let's take a look at the very last slides in this PowerPoint. And we'll take a look at a few consequences of knowing the wave-particle duality nature of matter, number one. And number two, being able to describe electrons as waves and as particles, and therefore the mathematics that allowed us to make maps of where electrons probably are. This mapping of where electrons probably are gave rise to a new mathematics called quantum mechanics. And the quantum mechanics allowed us to have 4 different quantum numbers. And the 4 different quantum numbers allowed us to graphically represent where electrons probably are. And where electrons probably are told to us by something called electron configurations, which give us the distribution of all electrons in an atom. The electrons configurations consists of 3 things. First of all, a number denoting the energy level. That's this big number 4 right here, which is also known as the principal quantum number n. A letter denoting the type of orbital, which is actually the azimuthal quantum number L, which can be 0 for S, 1 for P, 2 for D, 3 for F, and then lastly a superscript like this number 5 right here, denoting the number of electrons in those particular orbitals. Orbital diagrams have a box associated with each representing one orbital. Half arrows represent the electrons, and the direction of the arrow represents the spin of the electron. Typically, up arrow represents positive 1/2 spin, down arrow represents negative 1/2 spin, but it's not necessarily has to be that way. Hund's rule says that for orbitals that have the same energy, the fancy name for orbitals of same energy is degenerate, the lowest energy is attained when the number of electrons with the same spin is maximized. Well, what that means in layman's terms is that when you put electrons into an orbital like the 2p orbital, you first put one electron in each orbital of the same spin before they pair up. One electron in each orbital before they pair up. That's called Hund's rule of pairing. We fill the orbitals in increasing order of energy. Different blocks on the periodic table then correspond to different types of orbitals. Notice here's the S's, here's the D's, here's the P's, and here's the F's. The blue ones right here are called the representative S block. The pink ones are called the representative P block. And together, the pink and the blue make up what are called the representative elements on the periodic table. We'll talk more about that in Chapter 7. This area right here in kind of a peachish color are called the transition metals, and then down below here are the rare earth elements, or the F block metals. Some irregularities occur when there are enough electrons to half fill the S and the D orbitals on a given row. Chromium and molybdenum are examples of that. We would expect chromium to be 4s2, 3d1, 2, 3, 4. But as a matter of fact, chromium borrows, in effect, one electron from its s orbital and puts it into its d, giving it the electron configuration of 4s1, 3d5. Molybdenum does the same thing, except for in a higher energy level. Copper and silver do the same similar thing, where they can fill the d orbital and have a half-filled s orbital by borrowing, in effect, one out of the s orbital. Here's the electron configuration for copper. Because the 4s and 3 orbitals are very close in energy, they go ahead and borrow electrons. These anomalies occur a lot in the F block down here. Notice these F blocks should actually fit right in here. And in the true long form of the periodic table, the F block is in here, and it actually shoves this S block farther over. Notice how they use the core electron signification right here of parentheses Ne. If you look back at neon's electron configuration, written right here, it's everything that precedes it. And if you look at your Cadillac periodic table, they always use this core electron representation for ones that are further down on the periodic table because it takes less writing. and it's kind of a shorthand version. And since we're usually more interested in the outer shell electrons anyway, those allow us to get right at the electrons that are furthest away from the nucleus, which are the ones that usually react the most. So, in summary, this chapter, once again, from the very beginning, talked about the wave particle duality of nature of matter, and a consequence of that became the Schrödinger equation and dealing with this problem of electrons being waves and particles, or wavicles. And because of that, we came up with these things called quantum numbers. Quantum numbers in quantum mechanics describe where an electron probably is around the nucleus of an atom. And remember, we had various pictures that showed where these are. There was an s orbital that looked like a sphere. There were p orbitals that looked like dumbbell-shaped critters with 3 different orientations. And then there were d orbitals. Whoops, I think I missed the d orbitals up here. The d orbitals that had flower petal shapes, and remember there were 5 of those orientations. Then we used those orientations to say, okay, we can write the electron configuration, where electrons probably are, and give each one a unique set of quantum numbers, and say these are where the electrons probably are around the nucleus of an atom. And we can describe it using electron configuration. Lastly, we were able to draw orbital diagrams of these electron configurations using arrows and boxes to represent the paired and unpaired electrons in a particular element. In Chapter 7, we'll look at the result of this, and we'll say, okay, now that we know where these electrons probably are, how does that help us in the arrangement of the periodic table to determine how they will react or how they will act, and why elements are put together the way they are on the periodic table. Good luck with your electron configuration and orbital notation.